Good evening everyone. My name is Renuraman Sahu and today we'll be discussing about the density of states, Fermi energy and the electron specific heat at constant volume, and then we'll discuss some of the questions and answers that was discussed last week, uh, and that will help you to solve the assignment of this week. So we're talking about a model in the last class that represents how in the one dimensional case how an electron will look, uh, what the electron will feel inside a solid, and we had come up with this idea that uh, the electron will feel ionic cores. So there would be ionic cores, and each of these ionic cores will have a potential like this. And to model that one, we had come up with a square well potential approximation, something like this, where each of these well represents the ionic core. What we are going to do today is to try to understand how the energy levels are, we are going to look at a particular energy level. Let's say this is A. So we are going to look at a particular well and say that this is really very deep, so that the potential here, and like here is the well which we are taken out. We are going to look at a particular well and say that okay, this well is very deep, so deep that from here the height can be thought of as infinity with respect to this A. So it is a very large height with respect to A. That is why we are saying that this is infinity. Remember that this A is of the order of a few angstroms because it is the atomic length scale. So to solve for the energy levels in for the electrons in this well, what we have to do, we have to solve for the Schrodinger equation. So this is the Schrodinger equation, minus h bar square 2m, and the double derivative of the wave function psi with respect to the position x. So x is along this direction, plus v of x psi of x is equal to E of psi x. So this E is the energy eigenvalue. Once we solve this, we will get some values of E. That E is the allowed energies for these electrons. So if we try to find what is the wave function of the electrons outside the well, so it has to be 0, because if you remember from Born interpretation, the mod psi square is the probability of finding the electron. Mod psi square is the mod psi square probability density of finding the electrons in the region. So this is a function of x, right? So in the region x to x plus dx. So in this small region, so and now we are saying that okay, this is an infinite potential well and the electron is totally confined in here. So outside this, if you take any region, say x, at this position, here you will find no electrons. Okay, and mod psi square is 0 at that point. So the wave function is identically 0 wherever this v is infinity. So if this v is infinity, then the only way that this Schrodinger equation can be satisfied is when psi of x is 0. Then the left hand side and right hand side both are 0. And it has to be identically 0 because so there has to be no curvature of the wave function. So it is identically 0 up to this boundary. Now all we have to do is how the wave function is behaving in this potential well, or inside in the region from x equal to 0 to x equal to a, how the wave function is behaving. So inside here the value of the potential v is 0. So v is 0 here. So you put v equal to 0, and what you have here, and you take these terms minus h bar square by 2m to the right hand side. So you end up with d2 psi over dx square is equal to minus 2me over h bar square of psi of x. Now you see this equation is very much similar to the harmonic uh, oscillator, the differential equation for the harmonic oscillator. Here E will be a constant based on it is an eigenvalue that we want to determine. H bar is a constant, M is a constant, E will also be a constant because it is an eigenvalue. So so basically E is not a function of x. That is what is important. So since it is not a function of x, it is constant with respect to x. So we can so this can be satisfied by a function which is sinusoidal. So psi of x we can write it as a cos kx plus b sin kx. So cos and sin are the sinusoidal functions, and a and b are the arbitrary constants or the constants of integration. Now what we are going to do, we are going to take a double derivative of that. So once we take a double derivative of that, what we have is minus k square a cos kx plus b sin kx, and this is nothing but your psi of x. And when you compare this with this equation, so k square has to be equal to 2me over h bar square. So k square is nothing but 2me by h bar square, and then you get what is e. I mean you have to take this to the left hand side and rearrange it, and you will end up with e is equal to h bar square k square over 2m. Now we have the solution that okay, psi of x equal to a cos kx plus b sin kx, it satisfies the equation. Now we have to impose the boundary condition. So what would be the boundary condition? We have discussed that at this point the wave function is 0, and at this point the wave function is, so along this line wave function is 0 all the way up to here, the wave function is 0 all the way up to here. So at these two boundaries, at x equal to 0 and x equal to a, the wave function has to vanish to satisfy the boundary condition, and psi of x has to be continuous, it cannot be a discontinuous function. Okay, so since it is a continuous function, psi of x at here at this side of the boundary we know that it is 0, so at this side of the boundary it has to come to the 0. So psi of x equal to 0 is 0, and psi of x equal to a is 0. So now let us put the first, this is the first boundary condition, psi at x equal to 0 is 0, and psi of x equal to a is also 0. So when you put psi of 0 is 0, so a cos kx plus b sin kx, you put x equal to 0, so a cos 0 plus b sin 0. Sin 0 is anyway 0 and cos 0 is 1. So we end up with a is equal to 0. Now let us look at the other boundary condition. So first boundary condition gave us a equal to 0. What is the second boundary condition giving us? So psi of a is equal to 0. So now you replace x by a. So a cos ka plus b sin ka is equal to 0. Now from here we know that a is equal to 0. You just put it in here. So you are left with b sin ka is equal to 0. So b sin ka equal to 0. Now when is this 0? So we want this to be identically 0 for all values of b. So irrespective of, so this is an arbitrary constant that we can put any value. Okay, so it need not be necessarily 0. Okay, if it is 0 then there is no wave function at all. So the sign of Ka has to go to 0 identically, and that is possible only if Ka is a multiple of pi, an integral multiple of pi. So Ka is equal to n pi. So therefore K is equal to n pi over a. Now remember that this a is of the order of few angstroms, and this K, so as we'll see later, and what is this L? L is nothing but your, so if you remember this potential, so L starts from here to here. This is the boundary of the metal, and A is this. L is of the order of meters and A is of the order of few angstroms or nanometer. Okay, we are going to see that this, based on this distance, this A can be of the order of, now okay, see, A is of the order of nanometer. Now if the distance of this well it increased and it goes of the order of, let's say, meter, of the order of meter, so then these k values, so what do you have to think of this n values, like what would be the gap? The gap will be of the order of pi by a between each k values, because n are integers. And if it is of the, if the length of the well is of the order of l, then the gap between these k values is pi over l. Now see, if l over a is of the order of, this is 10 to the power, so this is 1 meter, of the order of 1 meter, and this is of the order of angstrom, so it is of the order of 10 to the power 9. So in the region, almost 10 to the power in the region of, for example here, if it is n pi over a is in the denominator, so the distance between k is significantly large, as much as 10 to the power 9, as compared to when you consider n pi over l. Okay, so this will have a very profound effect, we'll be going to see that. So here, what we see here the spacing between, so energy is a function of k, and k, so energy, we had found that energy equal to h bar square k square over 2m, this we already have found, and k is equal to n pi over a, we just put that in here, so h bar square by 2m, and k we are replacing with n pi over a and the square of that. So what we are getting here, so is, if the well is very very narrow, of the order of 1 nanometer, then this comes out to be of the order of some electron volts. And when this a is of the order of meter, like so when, if you replace a over l, a by the l, then it is of the order of a few meters, and the spacing between these k values, they will these energy values, they will be very very small, and it is small as 10 to the power minus 10 electron volts, that is very less in energy. So the band gaps are of the order of electron volts, but when and if you remember that this is the region where we say that electron is nearly free, and the, so yeah, this is the nearly free electron energy level. If you plot this energy with respect to k, what we have is E versus k plot, and it is a parabolic plot. And we'll say that, okay, since x-axis is k, we say that this is the k space representation of the energy. Okay, and we had taken only one dimension here, so n square was just one value. But if we take in 3 dimension, so what we'll end up with is n square is, we have to take the contributions from the confinement in 3 regions, so it will come up nx square plus ny square plus nz square, and E equal to h bar square pi square over 2ms square, and here in bracket nx square plus ny square plus nz square. Now what we have is, for a given value of energy, so let's say you fix the value of energy, and we are looking at what are the possible values of energy here. So if you look carefully, this will be the equation of a sphere, where this is in the space of nx, ny and nz, and we have this Fermi-Dirac distribution, this we have discussed in the last class, that it tells you about the occupancy of energy levels starting from 0. So like from 0 energy value to EF depends on the material, and this tells you only about the probability of occupancy. Okay, we want to find what are the density of the allowed states, that so that we define as dE. So there will be some allowed states in the material, and the Fermi energy, the Fermi-Dirac function, it will tell you what is the probability of occupancy. So it is like you have some seats in a stadium, and then there is another function which will tell you, okay, these are the seats which are, uh, uh, these are the probability of occupancy for the seats to be filled. So availability of the seat is not as the is not as the number of person which are occupying the seats. Okay, similarly, so these are the two notions we are developing here. So d of E is the number of states in the energy range from E to E plus dE, and n of E we are defining another function which will tell you it is the number of occupied states in the energy range E to E plus dE. So what are the occupied states? So how do you get that? So you find what is the number of states per unit energy range, number of, and that availability. So you have the states now. Now you multiply with it. What is the probability that it is occupied? So the probability that it is occupied is, you have to multiply with f of E. And why this two? This two is therefore for each given state there can be two spin states. Like for each given k state there can be two spin states. That signifies the value 2 here. And for two spins, spin up and spin down. Now all states of equal energy lie on the surface of a sphere that we have just seen, and E is equal to h bar square pi square n square over 2m a square, and n has to be a positive number. So that we want to count the total number of, so what is our target now? We want to find that d of E, the total number of states. So the total number of allowed states up to energy En is the volume of sphere in the n space in the first octant, because you see here nx has to be positive, ny has to be positive, and nz has to be positive. Okay, and that we will divide by what is the volume of a single state in the n space. So in the n space, so the volume of a sphere is what? 4 by 3 pi n cube up to the state n, and we are taking only the first octant. So that is why this 1 by 8 is there. So all the spheres, like if you think of it as think of this diagram as your n space, so the states are occupied only in the first octant. So it is 1 by 8 times 4 by 3 pi n cube, and for one state it is just occupying a volume of 1 here. And so simplify that, it turns out to be 1 by 6 pi n cube. Now the thing is, so we have a relation between the total number of allowed states up to energy En. So now think, so let us try to replace this n with respect to E. So we want to find what is this value with respect to the energy. Then we need to have a relation between energy and n, that we already have here. So E is equal to h bar square pi square n square over 2m a square. You keep n on one side and take all the other factors to the left hand side, and you end up with n is equal to 2m e a square over h bar square pi square. Now, so this is the number of allowed states up to the energy n. N corresponds to, so up to n means there is a like upper limit n and corresponding to that energy. So we are replacing this n by this function which will give you E in terms of n, or n in terms of E. So the number of allowed states up to energy En is like, what is it? 1 by 6 pi n cube. So 1 by 6 pi, and this is the cube of the n. So what we have just done is we have separated this E from the other factors. So 2m square over h bar square pi square 3 by 2 into E to the power 3 by 2. Okay, so this is the number of allowed states up to energy En. Okay, so the density of states, what it says? It says that density of states is the number of states per unit energy or number of states available from E to E plus dE, and if you integrate that from 0 to En, then you will be like you will end up with the function you will end up with the function which will tell you what is the number of allowed states up to energy En. Now that you have here already here, if you take the derivative of this with respect to E, then you will end up with dE. So that is what we will do now. We have this value, we'll take a derivative of this. So once we take a derivative of this, we'll end up with dE. So this function you have to look carefully. Take a derivative on both sides. So if you take the derivative, you end up with dE here, and if you take derivative here, what you have is 1 by 6 pi. So this 3 by 2, it is just 3 by 2 e to the power half. And if you simplify that, you will get d of E is equal to pi by 4 2m square over h bar square pi square to the power 3 by 2 and e to the power half. So what we have now is the density of states dE. It tells you what is the number of allowed states in the energy range E to E plus dE. So if you plot this with respect to E, what it looks like, it is e to the power half. So this is along E, and if you plot that, you will get this parabolic curve. So what you see here is at low energy there are less number of states, and as you increase your energy values, the number of states are also increasing. But that doesn't mean that so these are the available states. So these available states has to be filled up so that you get what is the number of electrons. And how do you know that? You know that by the occupancy, the probability of occupancy that is given by this Fermi-Dirac function. So Fermi-Dirac function tells that at 0 Kelvin, let us look at the case of 0 Kelvin. At 0 Kelvin, you have to like follow this red curve. So up to the Fermi energy EF, your states are totally filled, and after EF, your states are empty. Okay, so what we have to do to get the total number of occupied states or the states which are filled by the electrons, that you get when you multiply this 2Fe with dE. So 2 is a constant, so let's not much bother about it. So f of E dE, so it is 1 up to it is multiplied with 1 up to EF. So it is just this curve is just tracing like that, like that, like that, and when this f of E becomes 0, so it becomes suddenly 0. So the number of electrons between E to E plus dE is given by, so this n of E at this energy level you want to find. So this is the number of electrons between E to E plus dE. Okay, so that's the idea. So this red curve was at the case when the temperature was at 0 Kelvin, and the green curve is when your temperature is at more than 0 Kelvin, or it is like you have some finite temperature. Okay, so what you are getting is n of E as it is first increasing, and at the Fermi energy it starts decreasing. So what you have here is yeah, so and the energy starts decreasing. Not the energy. Yeah, the number of electrons which is occupied in the energy range E to E plus dE, it first increases and then it starts decreasing at the Fermi energy level. Now the Fermi energy, so we know what is a Fermi energy. Fermi energy is what at 0 Kelvin, what is the highest occupied state, or the state or the energy level which is the probability of occupancy as exactly 1 by 2 at some finite temperature. That is your Fermi energy. So based on this Fermi energy, we are going to look at some of the other parameters. Like we have this Fermi energy, so E equal to h bar square k square by 2m, that we already know. And in 3 dimension, what we will have is E equal to h bar square by 2m kx square plus ky square plus kz square. And what is this k? K is actually the wave vector 2 pi by lambda, and it has a units of 1 by L or length inverse. Okay, and if you look at this in the k space, we are keeping this on left hand side, and rest we are giving it like taking to the right hand side. Kx square plus ky square plus kz square equal to 2ma over h bar square. So for a given energy, the above constant, which constant, this constant, will say that it is a sphere of radius 2me over h bar square. Okay, so if you plot that in k space means all the x axes are of the units of k. So this is kx, ky and kz, and if you plot that, you will get a sphere. So all the k values that lie on this sphere, they will constitute something called the Fermi surface. So why this Fermi surface? Because like at a certain, so this EF is a particular energy, uh, so all the k values which are less than this sphere, which are inside this sphere, will have energy less than EF, and on this particular sphere the energy value is EF, and the locus of all the points which will constitute the energy EF is called your Fermi surface. Okay, so uh, so we define something called a Fermi temperature. How do we define that? So energy per particle, we know that it is like kBTF, and TF when kBT has the units of energy, and kBT when we equate it with the energy EF, then what we get, the temperature that we get is called the Fermi temperature. Okay, and so as we had seen, n of E, which is the number of electrons in the energy level from E to E plus dE, that is given by this function, and we see that EF is the highest energy electron at 0 Kelvin. Okay, so this is your Fermi temperature and Fermi surface. So we got to know what is Fermi energy. Fermi energy is the energy which has so we got to know this from that uh, from the plot, Fermi Dirac distribution plot. Then we saw the Fermi surface. What is Fermi surface? Because in it is spherical for an it is spherical in the k space. And we saw what is Fermi temperature when we equate kBT with respect to when we equate kBT to the Fermi energy. Then what we get is the Fermi temperature. Now what is temperature? Temperature represents the potential for the heat to leave a system. Similarly, what is pressure? Pressure is it represents a potential for the material to leave a system. If there is a pressure difference, then material will flow. If there is a temperature difference, then the heat will flow. And there is something called chemical potential. Uh, what this chemical potential it tells you is that it is particularly associated with a particular species. For example, in a sodium chloride solution, so sodium will have its own chemical potential, chlorine will have its own the chlorine ants will have its own chemical potential, and so on. So it is the measure of the chemical potential is the measure of a particular specific species in the solution or in the system to leave that particular phase. And this Fermi energy, it is the measure of the chemical potential of the electrons. So this Fermi energy, it tells us, so this idea is helpful particularly in designing the heterojunctions and so on. So it will tell you okay, how the electrons will move in and out of the system when you put two different materials with different Fermi energy together. So this concept is the Fermi energy as a measure of chemical potential, that is quite helpful in making heterojunctions, and like that will help you design in structures like LEDs, lasers, and so on. So there's a whole different bunch of physics into there. So the idea here is that EF has to be thought of as a chemical potential. So EF can be thought of as a it will tells us what will happen if two material systems with uh, different Fermi energy are brought together. So we learnt about the Fermi surface, the surface in the K space that represents the Fermi energy, and it is a particular wavelength. It has the units of inverse wavelength. So diffraction. So why all this was important? So this was important to study, like how do we probe a system? How do we know that what is the structure of a system? So these concepts will come into use when we try to understand a system by like probing it with some like some photons or some ions or some like there would be some probe, and uh, here we can define something called this lambda f will corresponds to, so k, so from ef you can get the kf from the relation h bar square kf square by 2m, and if you equate this k as 2 pi by lambda f, you will get your required value, this lambda f. And this lambda f, it tells you what should be the order of radiation source for the interaction. So if you bombard the probe, so your probe, that can be a photon or a neutron or any other source, if it has a de Broglie wavelength of the order of lambda f, then you will have some possible interaction, and by studying that interaction you will get to know what is the structure of the material. So you have a source, and then you have a sample, and you have a detector. So from source, that particular this the radiation of the order of lambda f wavelength should come, it should hit the sample, then whatever is scattered from the sample, you go and detect that one. So there can be other different types of, there can be different types of sources, like it can be an EM radiation, particularly in X-ray. X-ray it is an EM radiation. Some people also study the neutrons radiation or neutron scattering. So the sample with a periodic structure, if a sample has a periodic structure, then the we call it a crystalline structure, then the wavelength range should be of the order of that lattice spacing. Okay. So these are the few things we have discussed. So just uh, to understand what is the value of TF. So this energy EF is of the order of electron volts, and TF, if you put the value of the Boltzmann constant, and if you take it to the right hand side and calculate what is TF in Kelvin, so even at the ground state, TF is of the order of 10,000 kelvins. So now let us try to, so with this information and background, we can try to understand uh, what is the electronic contribution of specific heat at constant volume. So we had seen that, so what we had seen that in Drude model, the specific heat was overestimated by a factor of 100, and when we saw this is an anomaly, what we tried to do, we tried to put in the Fermi-Dirac statistics. We identified that electrons are the quantum particles, and since electrons are the quantum particles, they are identical and indistinguishable. Then we said that it also follows the Pauli exclusion principle, and then and this is the statistics it follows, the Fermi-Dirac statistics. And then we looked at how the states are distributed in the material, and we found out what is the number of electrons per unit energy levels. uh, yeah, per unit energy level. So this is the number of electrons at different temperatures, T equal to 0 Kelvin and T greater than T at T more than 0 Kelvin. So these are the curves that we have discussed. So what we did was, we found what is the number of states up to energy E, and then we took the derivative of that and found what is the number of states in between energy E to E plus TE. So we ended up with So these are the two expressions we had. The n of p, this is the total number of electrons up to total number of this is the total number of states up to energy E, and this is the number of states up to this is the number of states between energy E to E plus dE. So it is kind of a cumulative function, and this is you can think of it as an histogram, like from E to E plus dE, what is the number of energy states. Okay, now what you can do is, if you divide these two, d of EF divided n of EF, so you will end up with this value 3 by 2 1 by EF, and we want to find what is the density of states at the EF or at the Fermi function. Why particularly? Because we saw that, like, qualitatively we have seen what contributes to the electronic specific heat is the electrons which are available at which are closer to the EF, not which are uh, outside the EF or too deep within EF. Because if you try to excite a material from excite the electron from here, it will have no energy level to go up here. And remember that this thermal energy is of the order of like some millikelvin. For example, in room temperature it is of the order of 26 millikelvin, 26 sorry MeV, milli electron volt, and EF is of the order of 2 electron volt. So this smearing that you see, that is actually of the order of so this range from here, the spinning starts from here to here, that is 10 to the power minus 3 times or 1000 times smaller than this spacing. So it is a very small fraction of electrons which is actually participating in raising the temperature of the system. So what we want to find, what is the density of states at EF, and what is the total number of states, occupied states, up to energy EF, and that we are dividing, and after dividing we are ending up with d of EF over n of EF is 3 by 2 1 by EF. So d of EF is 3 by 2 n EF by EF. So what is this? D of EF is 3 by 2 times the number of states the number of occupied states up to energy EF divided by EF. That is what we have. Now let us try to so the total number of states available up to the Fermi energy is n of EF. So these are the so these are still the number of states. Okay, so d of F equal to 3 by 2 n of EF by EF. That is what we have found. And then what we are saying is only the electrons within the kBt of EF can gain energy when temperature is raised to T. So when you have a certain raise in temperature, only these electrons can come hop into here, because here there are empty states. On the other hand, here the states are not empty. If you try to excite this electron, it will end up with another occupied state, so it cannot go to that energy level. So electrons which are at these energy levels, which are closer to EF, they can only hop to the other electrons, to the higher state. So the number of electrons that can participate in the process are this d of EF, which will tell you about the number of states at energy EF, times kBt. So basically, so what we have is d of E is the number of states in between energy E to E plus dE. Now we say that this dE is nothing but your kBt. So what we have is d of E, dE is the number of states. So this is the total number of states. Okay, this is the number of states in energy E to E plus d E, or E to E plus kBt. So this is no more the density of states, this is the number of states. Okay, now if you do d of E kBt, this is the number of states in the interval, this is the number of states in this interval, sorry, in this small interval. And dE we had seen that it is 3 by 2 n of EF by EF. And what is n of EF? This NEF is the total number of states which is occupied up to energy EF. So up to energy EF, all the states that are occupied, that is covered here. Okay. So the gain in energy, so what is this quantity? This quantity is nothing but your number of available states that can interact with the temperature kBt. Okay, so why we have taken d of EF? Because only at that neighborhood it can interact with the temperature. So the gain in energy by the raise of temperature is the number of electrons participating in the process, which is this, times the energy gain per electron. So E is equal to 3 by 2. So this is what we are replacing in here. And what is the gain of energy per unit electron? It is 3 by 2 kBt. So this we are just thinking as whatever the electrons which can take the energy, it will behave as a free particle. So 3 by 2 kBt. And when we take the energy, so so if you multiply that, it is E equal to 9 by 4 NF over EF kb square T square. Okay, so now what we have here is E is equal to this expression. This expression is for E. Now CVE is equal to dE by dt. Now if you take the derivative of the temperature, you end up with this expression which is covered in this square bracket. So what we have here is the expression for expression CVE. It is linear in temperature. So this is one of the success that the Sommerfeld model can tell. Okay. Now the electronic contribution to the specific heat at constant volume. So this is what we have. Now EF is equal to kBTF. We just replace this EF by kBTF. So when we do that, so we end up with kBTF here. KB cancels KB, and what we have here is 9 by 2 NF KB T by TF. Now TF, you remember, it is of the order of 10,000, and T is of the order of 300 Kelvin. So and what we have here is, earlier in Drude model we had that CVE is 3 by 2 NKV. Here it is NF KB T by TF. So there is this factor of T by TF. Remember, this NF is the total number of states up to energy EF, and all those states up to energy EF are filled. That means this gives you a total number of this gives you an idea of what is the total number of electrons in the system. Okay. So we have in the Drude Sommerfeld model, it is 9 by 2 NF KB T by TF, whereas in the Drude model it was 3 by 2 NF KB. And most of the contribution to the specific heats comes from the electrons between 0 to 1 Kelvin. So to understand this, we get, so why this is important? Because so this is the only the electron specific heat, and to get only the electronic specific heat, we have to understand that it is mostly the electrons contribute to the specific heat only when we cool the temperature. When we cool the temperature, then lattice vibrations they all subside, and the only electrons are in excited state, and they contribute to the specific heat. So now here we have this T by Tf factor extra, and if you remember that T is of the order of 300 Kelvin at room temperature, and Tf for most of the systems it comes out around like 20,000 Kelvin, and if you do that 2 by 2f, it is of the order of 10 to the power minus 2. So this tells us that the CVE is 9 by 2 NF kb T by Tf. This factor of 10 to the power minus 2 that solves the problem that in the Drude model it was overestimated by a factor of 100. So that solves the problem of electronic specific heat, and so what we did to summarize is, so we had Drude model, it had problems. The problems, one of the problem was this very high contribution of the electronic specific heat. So we put in the Fermi-Dirac statistics, and we got the Drude-Sommerfeld model, and in this Drude-Sommerfeld model we solved the problem of CVE. Okay, and till now what we had was the electrons, those electrons, so even in Sommerfeld model as well as in Drude model, the electrons behave like they are contained in a room. They are contained in a room, and there is no sense of directionality anywhere the electron can go. But in reality, we see the properties of material, they are anisotropic. Okay, a property measured along one direction in the material is different from the other direction in the material, and this is attributed to the fact that the electrons actually see the ionic cores, and that we had come up with this kind of model. Okay, and what is inherent in the material is, so why this anisotropy can be there? This anisotropy can be there because of something inherent in the material. So, and what is that? So electrons are, it is available in all the material. Like given any material, we will find electrons. It is like a universal particle. But what is inherent to a particular material is its crystal structure. I mean the way in which the atoms are arranged in that crystal. So what we have here is a model we had built to understand how the electrons are distributed in how the ionic lattice can be modeled, and we have seen that so these wells can be thought of as the ionic cores, the location of the ionic cores, and they are separated by some distance, that is called a lattice spacing. And electrons which are in the metal but outside of this ionic cores, I mean these are the valency electrons, they are free and they can move all around in the material. So those electrons are called nearly free electrons. Okay, and the electrons which are which can exit the metal, they are called the free electrons, the actual free electrons. So now what we have here is a real space depiction of the ionic system, of the ionic cores. But like we had seen that what we have seen is energy can be represented E equal to h bar square k square by 2m. So and this k is nothing but your de Broglie wavelength. Okay, and this tells you about what should be the order of your wavelength which will interact with the system. And therefore, if we can somehow represent this system in the space of k has 1 by length or reciprocal of length. So the space of k is also called the reciprocal space. And if we can somehow determine this arrangement in the reciprocal space, then we can actually get a lot of information about the interaction of the crystal structure with the external probes and how the electrons behave in it as waves and so on. So these waves interact, so the waves which will be interacting with the ionic lattice, so how do we understand them better? By going to something called a reciprocal space. Why reciprocal? Because it is the reciprocal of length, and that k value in the k space we are going to see, that is why the k space is also called the reciprocal space. Okay, so now based on this discussion, some we can discuss some of the questions and answers. So the Fermi surface in 3D case space. So we had just seen what it is. The Fermi surface in 3D. So what is Fermi surface? So we had this relation, right? 2me over h bar square is equal to kx square plus ky square plus kz square. So this is a three-dimensional spherical surface, right? So the correct answer will be it is spherical and it is in three-dimensional. So what is the relation between the Fermi energy and Fermi temperature? So what is Fermi energy is EF, and Fermi temperature, how do we find? We do KBTF. So it is kind of, so it is a linear relationship. Okay. So the Drude model over predicts the electronic contribution to the specific heat by the order of, we just saw that CVE in Drude model is 3 by 2 NFKB. Okay, but actually it is 100 times the actual value. So where this 100 it came from, it is like T by TF, if you remember. T. So in Drude summer, this is in Drude model. But in Drude Sommerfeld model, there was this term 309 by 2 NFKB T divided by TF. Okay, and this is of the order of 10 to the power minus 2. So it over predicts the electronic contribution to the specific heat by the order of 10 to the power minus 2. The relation between DE and E. So what was the relation between DE and E? The DE is this and E is this, and the relation between that is this. Okay, so DE goes as e to the power 1 by 2. Okay, so and this is kind of a parabola if you look here, so that is why it is parabolic. And the occupied states is it is also, it will behave also, it will also behave like the same. How same? Because like if you plot n of E will come here like that. At the Fermi temperature it will go like this, but the behavior will still follow the same trend. It is no, so it will follow this parabolic trend. Okay, so as the material temperature is increased, only electrons dash to the Fermi energy are able to participate in the specific heat process. Now if you remember this, diagram, E and N of E, so these are the electrons which have occupied the energy levels, and this is E, F. So this is at 0 Kelvin, and if you want at a higher temperature, it is like so. This is the KBT range. If you try to excite some of the electrons here, and so then you reach here, and this is already filled. Since it is filled, so anywhere else you cannot, since it is filled already, you cannot excite these electrons. So below EF it is not possible. Above EF there are no electrons to excite only. So above is also it is false. And far from EF is like too further than KBT. So there also it is filled here and there are no electrons on the other hand side. So this is also not true. So the only thing is it is closer. It has to be near that KBT range. Okay. So the density of allowed states for an electron in a metal. So how do we find this? So let us plot what is the density of allowed states. The density of allowed states is d of E on this axis and E on this axis. So it looks somewhat like this. Okay. Now the thing is more at the Fermi energy. So Fermi energy would be somewhere here. EF, EF. Okay. The density of allowed states for an electron in a metal is more at the Fermi energy than at lower energies. So it is lower energy is somewhere here. So and the density of states is obviously more at the Fermi energy. Okay, so this statement is correct. It increases with increase in energy. You see, with increase in energy, it is increasing. So it is also correct, and it is independent of the density of occupied states. That is true. So what is density of occupied states? N of E is equal to 2F of E times D of E. So D of E is your density of occupied states, and F of E density of allowed states. And when you multiply that density of allowed states with 2 into Fe, or the probability of occupancy, you end up with the density of occupied states. So that is a different quantity. It is a different quantity, and this is a different quantity. So it is independent of the occupied states, and it is dependent on the probability of occupancy. So no, it is not at all dependent on probability of occupancy. So D of E, it just depends on what is the material system. So whatever is the material, it will have some density of allowed states. Filling it or not, that is that will depend on what is the probability of occupancy. Okay. So it is not dependent on probability of occupancy. So according to the Sommerfeld model, the free electron contribution to the specific heat at constant volume is, so what is according to the Sommerfeld, the free electron to the specific heat. So CVE was what? 9 by 2 NF KB T divided by TF. Okay. So it is equal to the classical Drude model. That is totally false, because in the classical model, what we had in classical model, CVE, I'll just write only Drude, is 3 by 2 NFKB. Okay, but in Drude Sommerfeld model, we have this extra factor T by TF. Okay, so that is why it is wrong. It is greater than that of classical Drude model. Okay, let us see that. So this TF is of the order of 20,000 Kelvin, and this is of the order of 300 Kelvin. So this T by TF is of the order of 10 to the power minus 2. So it cannot be greater. Okay, but it is less than the classical Drude model by a factor of 100, because this 10 to the power minus 2 factor is there. And it is impacted by the Fermi temperature of the material. Yeah, that is true. Why? Because now we have this TF at the denominator, which is the Fermi temperature, and it is impacted by that. Okay, now we'll go to the next question. A system comprised of two materials and be kept at room temperature at constant pressure. The chemical potential of the electrons in the system will dash when A and we are brought together, brought in contact with each other. So what will happen here is that, see, this EF, it has to be thought of as the chemical potential of the electrons, or it will tell you, like, if two species are brought together, two material A and B are like brought together, then their Fermi energy will so adjust, or the chemical potential will so adjust, that there will be no flow of electrons between the materials anymore. So what will happen? So the chemical potential of the electrons will then try to become the average of Fermi energy of A and B. Okay, when they will become the average, then there will be no flow of the electrons. Okay, so that's the answer. Okay, so the wave vector corresponding to the Fermi surface of a metal at 0 Kelvin. So let us understand what the question is saying. So wave vector is what? Kf. How this is related to the Fermi energy surface? Ef equal to h bar square kf square by 2m. Kf is 2 pi by lambda f. So this corresponds in the k space kx, ky and kz. So it corresponds to the longest wavelengths permitted for electrons in a metal. Okay, so this is your Fermi sphere, and kf is inversely proportional to lambda f. The highest kf possible in the material is the highest k value, or the highest wave vector for the electrons permissible in that material is your kf. So highest kf means it has to be the shortest wavelength. So it corresponds to the shortest wavelengths permitted for electrons in the metal. So this is your correct answer and not this, because kf and lambda f are inversely related. And it corresponds to the largest magnitude of wave vector. So yeah. So what is happening is the largest value of kf is this. So it is the largest magnitude of wave vector permitted for the electrons in the metal. Okay, so the Drude Sommerfeld model says dash participants in the process of gain of energy on increasing the temperature. So this we have seen, it is the only the electrons which is close to the Fermi energy. And okay, so the electrons just below the Fermi energy, so this is also true, because just below the electrons just below the Fermi energy are close to the Fermi energy only. And another thing, so in the process of gain of energy, all the electrons, no, this is not true. Why this is not true? Because the electrons which are deep within the Fermi energy, they do not participate in the process of increasing the temperature. Now what about the nearly free electrons? So we'll just try to understand this with this diagram. So F of E. So this is your EF, and here at some temperature T greater than 0, some of the electrons are spilled over to this region. So now you see this EF is a bit, so the energy of these electrons is more than EF. So here the energy is more than EF. Now if you remember this diagram, it is filled with electron Like these are your nearly free electrons. Okay, nearly free electrons, this is your EF. Okay, so now this EF, so electrons here, they are, what are they? They are your nearly free electrons. So that is why the nearly free electrons is also a correct answer. Okay, the classical Drude model over predicts the electronic contribution to the specific heat at constant volume. So that is true. So we have seen that CVE in classical model is 3 by 2 NFKB, which is greater than the actual value by a factor of 100. So CVE, so this is Drude. Okay, this is actual times 100. Okay, so this is true. Two metals A and B have Fermi energies 1 electron volt and 2 electron volt. Which of the followings are definitely true about these two metals? So B has higher atomic number than, see here what we have to look at is the, so what we have to look at is how the electrons are distributed in the material. So it is not about the atomic number which plays a very critical role in determining the uh, what is the Fermi energy. Rather, it is the arrangement of the atom or the crystal structure that will tell you what is the Fermi energy. So the crystal structure and what is the availability of the free electrons. So the number of electrons that are there. So the number of electrons that are there and your crystal structure, that will in fact determine your Fermi energy. It is not the atomic number itself. Okay. So let us try to okay. So B has higher density than A. So this is wrong. B has higher density than A. So the density also further depends on what is the atomic arrangement, not the atomic number itself. Okay. So this also we cannot say. B has more free electrons per unit volume than A. Okay, so how is the number of electron? We have seen the number of electrons per unit volume is like N of E is 2F of E and dE, right? So what we have here is, so when we're talking about the free electrons, EF here is EF, this Fermi energy, it is given by 3 pi square n to the power 2 by 3. Okay, so more the number of free electrons, so here n is the free electron. So if you look at this expression, so there was an expression where energy was expressed as a function of n. Yeah. So this, what is this n of n? It is the number of allowed states up to the energy En. So up to energy En, if you put this En as Ef, it will give you the number of allowed up to Ef, means all the electrons are filled up to Ef. So the number of allowed states will be the same as the number of electrons itself. So the number of electrons up to energy En is that is your total number of electrons, and it is per unit volume. So number of electrons per unit volume, it goes as e to the power 3 by 2. So this e goes as n to the power 2 by 3. So that's what it is. So what we have here is, so B has what, 2 electron volt as Fermi energy. So it has more free electrons in it. Okay, or what you can think of it as, since there are more electrons and there is Pauli exclusion principle valid in it, so it will start filling, and it will require more EF. Okay, so you can think of it in that way. So B has more electrons per unit volume than A. So it has to be like, you have to remember that B, this you have to think of it as it is the free energy levels which are contributing to this free electrons, and not the ones which are bound to the atoms. So what, in our analysis, what we had seen is, we are talking about this ionic cores. So there are ionic cores and there are electrons which are roaming around freely. Okay, and it is this behavior of the free electrons which we had uh, talked about in our discussion. The one which are bounded, that we just told that it uh, it is not moving, and it is just localized to this ionic cores. So it is not the it is not the electrons per unit volume, rather it is the free electrons per unit volume. Which property of electrons help in studying the periodicity of the lattice inside a material? So the periodicity of a lattice inside a material, it is determined by the what is the value of its lambda f. So the property is so where is so it is, you need to have that wave nature of the electrons which is interacting with the so there has to be a wave which will be interacting with that lattice. This, if the lambda f is of the order of the lattice spacing, then we'll get some kind of interaction. So basically it is the wave nature of the electrons. So the wave particle duality of the electrons help us to study the periodicity of the lattice inside the material. In the Sommerfeld model, the number of electrons per unit volume which can participate in the process of raising the temperature of the material. Okay, so the number of electrons which can, so we have to find what is the number of electrons. So the number of electrons is given by what? The density of states at EF, and the density of states of EF times the K, what is the temperature? Okay, yeah. What is the range of that temperature? KBT times D of EF. So what is D of EF? This we had found that it was 3 by 2 NF by EF into KBT. So your correct answer is this. The wave function value of a deep potential well. Okay, so now it is asking about what is the value of wave function value for a deep potential well. So this is your deep potential well, 0, x equal to a, and this is deep means you can think of it as infinity, and we know that the wave function value is 0 0 0 up to here, and it is 0 outside the well, but here there can be some kind of sinusoidal function. It can be like this or it can be like this, but it is not identically 0. Okay, so the wave function value is 0 at x equal to a. At x equal to a it is 0, which is correct. It is 1 at x equal to a. This is totally wrong. It is 0 at x equal to 0 and 1 at x equal to a. So this is also wrong. 0 at x equal to a and 0 at x equal to 0 and 0 at x equal to a. So this is correct. This is the correct boundary condition. So this is all about it. Thank you. We'll meet in the next session.